In the first half of the vector spaces chapter, there are these items, and I guess I'll bring one up and then I'll have to move my head out of the way. But there are these learning standards where one of the goals is to take an assertion about linear dependence or an assertion about linear independence and turn that assertion into a statement about a vector equation. Right? So write a statement involving a vector equation that's equivalent to the claim below, and then determine which of these statements is true. And so the purpose behind this learning standard, this is V5, but V3 on spanning sets is similar, V6 on basis is similar as well, is just to get us to translate between this English language assertion about linear independence or about being a spanning set and translate that into sort of equation lingo so that we can get it into a form that we can use the tools of linear algebra to investigate. So I think, why don't we do this? Let's look at these two assertions that we would have to prove. And instead of framing them in terms of linear independence, because linear independence is kind of a statement about uniqueness of solutions to a certain vector equation, right? The uniqueness of the solution to the homogeneous vector equation involving those vectors. But it might be easier to negate the definition of linear independence and work instead with the definition of linear dependence. So these might be easier in their negated forms. In other words, the contrapositives of each one. So let's write out what those contrapositives would be. I'm going to call them 3 and 4. So what would the contrapositive of the statement, if W doesn't belong to the span, then the augmented set of vectors is linearly independent? What would the contrapositive be? What's nice about negating these things is that it's a lot easier to use the definition of span to say if W does belong to the span, then there exists a linear combination of the vectors in S that produce us W. Same thing with linear dependence. It means that there exists a non-trivial linear combination of the vectors in our set, which gives us the zero vector. Right? So there are that's sort of how this gives us a foothold into a positive statement instead of a negative statement, because working with independence and working with not belonging to a span, those things are harder to do. So let's pick one of these implications, and then I just kind of want to scaffold out what that might look like. Let's take number 3, proof of number 3. So what we would want to do here to set the context is that if we want to prove this statement directly, what we would do is assume that the hypothesis is true. So assume that my augmented set of vectors is linearly dependent. Assume that S union W is linearly dependent. We wish to show that W belongs to the span of S. Okay. So let's unpack that. What does it mean for W to belong to the span of S?
There exists a linear combination such that that linear combination equals W.
Yes. So there exists a linear combination of, in this case, a linear combination of the vectors of S, of which there are a total of m, right? So C1 up through Cm. So there are m scalars such that C1 times the first one of my vectors plus C2 times the second one of my vectors plus, and so on, up to Cm times the mth one of my vectors is equal to W. Right? So that's what it means for W to belong to the span of S. And so this is my burden of proof. If I can find constants C1 up through Cm such that this equation is satisfied, then we will be good to go. Right? Okay. So if that's what we need to prove, so I'm just going to kind of write it in here. Our burden of proof is to establish the existence of those constants. We call them scalars. I've been using the word constants a lot today, but probably I should be calling them scalars. Okay, so how do we know that such scalars will exist? Probably we're going to have to make use of this assumption, right? The assumption that my augmented set is linearly dependent. So what is the definition of linear dependence?
There's multiple solutions to our homogeneous equation.
Yeah, there are multiple solutions to the homogeneous equation, and namely the homogeneous equation is, I'm going to call it x1 v1 plus x2 v2 plus, and so on. It goes up to the last vector in the set S, so x sub m, v sub m. But then my set also has w in it, and so we have one more x sub, let's call it m plus 1, w is equal to the 0 vector. Oops. And backslash got messed up there. There we go. So there are multiple solutions to this homogeneous equation. So here's the thing that we're going to be assuming, right? And then here's the thing that we need to be proving. So we just have to figure out what route is there from point A to point B, right? How can I take the thing that I'm assuming, which is that thing, and make it look something more like the thing I'm trying to deduce, which is that thing? What might be a way to get it a little bit closer?
Do you mind screen sharing again?
Oh, you're right. I'm sorry. I forgot to share screen. Let me click that button again. There we go. So here's the thing that we've assumed, right? Because of our linear dependence, that we have this equation. It has multiple solutions. It has a non-trivial solution. And then here's the thing that we're trying to establish. We want to show that there exist scalars such that this equation is satisfied. So what's the biggest difference between these two equations? Maybe there's kind of a place to start.
Where W is?
Yeah, in one of these equations, W is the subject of the equation. That's in the second version of it here. In the other one, W is just another one of the crowd, right? Just another one of the vectors that's a part of this set, which we're saying is linearly dependent. And so the focus, the spotlight is kind of on W in the second version, but it's not really in the first version. So in the first version, because it's what we're assuming, what could we do to kind of make W the subject of that equation?
Could you move it to the other side?
Yeah, subtracting it to the other side. And so if I do that, I'm going to get an equation that looks like... So it's going to look an awful lot like the previous one, right? Except that we've got the right-hand side is going to be negative x sub m plus 1 times w. So this part is probably happening on scratch paper or something, right? That we're kind of doing a little bit of work that's going to show how we're going to get to the proof that we're trying to get to. So this looks a little bit better. And if I want it to look even more closely resemblant to this one, then what else could I do?
You could then divide by the negative x sub m1 scalar.
Yes. So if I divide by it, then I'm going to have, hopefully this works here. Oops. What's it doing? So I'm just going to copy paste that code, and some stuff keeps getting screwed up when I do that. I don't know why. Minus x sub m plus 1. So if I divide by the minus x sub m plus 1, then that minus x sub m plus 1 is going to become a part of all of my coefficients. X sub m plus 1. Right, so all my coefficients will flip sign and get divided by x sub m plus 1. and so on, minus x sub m over x sub m plus 1. Okay, and so this looks an awful lot like an equation that shows me that W is a linear combination of all of my V's. There is a wrinkle that we're going to run into in just a second. So if we happen to have done a legal division right here, then we are all set. So I think what we can do then is make this into a cases proof, case 1. And the first case is if x sub m plus 1 is not equal to 0. So as long as x sub m plus 1 is not equal to 0, then this thing that we just wrote that equation shows that W is a linear combination of the vectors in S as required, right? I suppose I should spell that out just a little bit more. So W belongs to the span. That is, after all, what span is. It's the set of all linear combinations as required, right? Let me just clean up this equation because it's losing subscripts for unknown reasons. There, that looks a lot better. So as long as that coefficient that we end up needing to divide by is non-zero, then we are in good shape, right? We've shown that W is a linear combination of the vectors in S. So let's handle the wrinkle. We have to convince ourselves that it's also okay if that m plus first coefficient is equal to 0. Because if that coefficient is equal to 0, I'm going to put up here, as long as x sub m plus 1 not equal to 0, we can divide at this stage. But if it's equal to 0, then I can't do this division step. So we have to figure out what this coefficient being 0 is actually going to mean. If that m plus first coefficient is equal to 0, then the fact that this set was linearly dependent requires that there's multiple solutions to this homogeneous equation involving the vectors in S, but also W, right? But if this m plus first coefficient is 0, then replacing that coefficient by 0 in this equation, right, really just tells me there are multiple solutions to the homogeneous equation involving not the vector W, right, involving just the vectors from S. So we can just erase that 0W from this equation. And my subscripts worked this time. That's interesting. But this cannot be the case, since by assumption, the set S, which consists of these V vectors, dot, 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 Vm, was linearly independent. Right. So in case number 2, in the bad case, you know, where we would not have been able to divide by this coefficient, we rule out the bad case here. It can't possibly happen, because in order for that bad case to happen, my original set of vectors, my S, would have to have been linearly dependent. But we start the proof by assuming that it was linearly independent. That was part of the premise of the statement, right? Suppose that this is a linearly independent set of vectors. Maybe I'll add S to the original statement here. So it's part of the premise of the problem that we start with a linearly independent set, and then we throw in another vector. So I think then we can put our little end of proof marks on each of those pieces.